All right, so this problem reads, in my neighbor's Boy Scout troop, they wanted to make an air rocket. They used compressed air to fire the 50-gram rocket vertically upward. The tube was 1 meter long, and the air exerts an upward force of 20 newtons on the rocket as long as it is in the tube, so that full 1 meter length. How high does the ball go above the top of the tube? All right, so this question is asking about how high. That's a kinematics property, so that's motion. So we're going to start the motion process. And the first part of that motion process is to identify the object, and in this case, that object is the rocket. So how high that rocket is going to fly up into the sky. We want to define the initial. So when do we start caring about the motion, and when do we stop caring about the motion? So we are interested in how high it goes. So we know that we care when it stops, when it reaches the peak. And whenever we're doing kinematics, we want to remember that that is a assumption of constant acceleration. So that means we are really interested in that kinematics problem once it leaves the tube, in order for us to assess how high it's going to go. Once it's in free fall, only under the influence of gravity. So the initial is when it leaves the tube. All right, so defined our problem. Now let's draw a picture. So we have our tube, we have our little rocket gonna fire up, and it's gonna go somehow, some height into the sky. In our picture, we have to define the origin and our coordinate system. So we're going to say that the upward direction is positive in our coordinate system. All right. What type of motion is this? 1 or 2 dimensions? Well, it's only moving vertically, so it's 1 dimension, 1 object, 2 objects, multiple phases. For this problem, it's a single phase, 1 dimension in the vertical axis, and 1 object. All right, so we're going to make our list, our initial position, our final position, our initial velocity, our final velocity, our acceleration, and our time. So our initial position, that's 0. It's right at that rocket exit. Final position, we don't know. Initial speed, we don't know. Initial velocity, we don't know. We do know it's in the upward direction, so we do know it's positive non-zero. Our final velocity, okay, it's reaching its peak. So right at that peak, we know it hit 0 meters per second. It's in free fall in this situation, so that's negative 9.8 meters per second squared for our acceleration. And we don't know the time. Now, what are we interested in? We are interested in solving for the height, this final position. If I don't know my time, I don't know my initial final velocity, I know my final velocity, and I know my acceleration. If I don't know my time, I'm probably going to use this relationship, which does not depend on time, and I'm interested in that delta x. V final is 0. I don't know V initial, but I do know 2 times negative 9.8, and delta x is what I'm interested in. All right, so in order to solve this, I need V initial, which means I need to know the speed of that rocket as it leaves the tube. Okay, well, speed is another kinematics problem. So since I need V initial, I'm going to go to my second kinematics problem. In this case, the object's still the rocket, so that transfers over. My initial and my final are what I'm interested in. I want the initial velocity of the rocket is the final velocity as it leaves the tube. All right. Where does it start? In the tube. So this is at the bottom of the tube, if I think about this problem. All right, so that's a new problem I'm thinking of. It's still 1 dimension. Now it's receiving a constant acceleration due to the force inside the tube, so I still have kinematics applying in my 1 dimension constant force, single object, no phases. So I can draw a picture. So now my picture is, here's the rocket. And we're going to call the bottom of the tube my position, x equals 0. And so we'll make our list. All right. So my initial position is 0. My final position, we know that tube is 1 meter tall. So my final position is 1 meter. It starts at rest in the bottom before that force is initiated. We don't know the final velocity. We don't know the acceleration of that force, and we don't know the time. So what are we interested in this situation? Well, in this situation, we're interested in final velocity. Remember, final velocity of this part is the initial velocity of this part, which is what I needed to get delta x. So again, we don't know time, so we'll probably be interested in using this relationship. V final squared is equal to V initial squared plus 2a delta x. My V final squared is what I'm interested in. V initial 0 squared plus 2. I don't know my acceleration, but I do know my delta x is 1. So in order for me to get my final velocity during this motion, I need to know my acceleration. Well, that acceleration is being caused by a force. So let's do a force analysis to see if we can get that acceleration. All right, so in a force analysis, I'm going to identify my object. Again, it's the same one, the rocket. All right, and so we want to draw a free body diagram of that rocket in this chute. So we're going to do a free body diagram of the rocket. And we want to think of the forces acting on that rocket. So we know that there is the force of gravity. That's between the rocket and the earth. And we know that points down, so I'll draw my force of gravity. That's, of course, equal to the weight, which is equal to mg. We also know that the air is causing an upward force on the rocket. I'm going to make it a little bigger. All right, so we have the force of the air, and that's between the rocket and the air, and that's in the upward direction. And we are told that that is equal to my 20 newtons. So there's my 20 newtons. Now we're only interested in the vertical motion, so we're gonna assume for this problem that there's nothing really happening on the side. So I'm gonna identify my forces, force 1 and force 2. No horizontal, so we're just gonna look at the vertical forces. Force 1 is pointing in the downward direction, so that's minus mg. And force number 2 is the positive direction. That's the force of the air. All right, my next step is to sum my forces and set them equal to mass times acceleration here in the vertical direction. So I have the force of the air minus mg is equal to m times the acceleration, and that's what I'm interested in. So we're told the force of the air was 20 newtons. The mass is 0.05, so 50 grams or 0.05 kilograms times 9.8. And that's going to equal 50 grams or 0.05 kilograms times my acceleration. All right, so we have 50 or 0.05 times 9.8. That's going to be 0. I could have probably done that in my head. We have 20 minus 0.49 is equal to 0.05a, and 20 minus 0.49, so I subtract 0.49, divide by 0.05, I get an acceleration of 390.2 meters per second squared is equal to my acceleration. All right, once I have my acceleration, I can solve for my V final squared. So V final squared is equal to 2 times 390.2. So I can multiply that by 2 and take the square root, and I get V final is equal to 27.9 meters per second. And once I know V final, I can solve for delta x. So we have V final is my V initial. So I'm going to move this to the other side. 2 times 9.8 is 19.6. So I have 19.6 is equal to times delta x is equal to 27, and well, that was that number, but 27.9 squared. So I want to make sure I have enough room here. Delta x, when I solve for that, is equal to, so 27.9 squared divided by 19.6, 39.7 meters. All right, that all fit on the screen? It did. Okay, so just to again reframe that problem, first we have to recognize that we have a kinematics problem. We're interested in how high something goes. It's maximum height, couple of assumptions. One, its maximum height means I have 0 final velocity, that peak, and I'm in free fall. If I truly am in free fall, in this case I am. So negative 9.8 meters per second is our acceleration. This tells us I need to know what that speed is, that velocity out of the tube. Should be velocity if we're working in vectors. So I need to find that velocity out of the tube. That too is a kinematics problem. When the acceleration is due to that air force that's happening, so I solve the kinematics for that. I recognize that, lo and behold, I need my acceleration. My acceleration is due to that force. I do my force analysis. I'm only worried about the force of the air up and the force of gravity down, recognizing that a 50-gram rocket is just 0.05 kilograms. We want to keep that in that standard unit. I can solve for my acceleration. My acceleration then allows me to solve for the final velocity as the rocket exits the tube, which is the initial velocity as it enters the air, and I can solve for my maximum height. Pretty good rocket for those Boy Scouts. All right, good job.